Hey all, as promised, here's a Cram video for the upcoming A-Level Chemistry Paper 3. Now, word of warning, not very long to make this one, so I'm using the relevant bits from the videos that I've already made for Papers 1 and 2, with a few extras thrown in. Just a reminder why I make them, it's because of messages like this, and I've been thinking if anybody wants to get in touch after results day and say something along the same lines as this, as long as you feel like the videos have helped, then I would absolutely love to hear from you, and I'll use your message in my Cram videos for next year. Okay, let's get into it. So I'm going to start with the ideal gas equation. So things to remember here, well obviously the equation is PV equals nRT, and you need to know your rearrangement. So let's say you ask for the pressure, it's going to be nRT over V. If you ask for the moles, it's going to be PV over RT, and so on. So know your rearrangements for the ideal gas equation. The units, pressure has to be in pascals. It's often given in kilopascals. The volume has to be in cubic meters. So if your volume's being given in centimeters cubed, you have to multiply it by 10 to the minus 6 or divide by a million. If the volume's being given in decimeters cubed, you've got to multiply by 10 to the minus 3 or divide by 1,000. R, the gas constant, 8.314, that's on the data sheet. So you don't have to remember that number, it's given. The temperature has to be in Kelvin. So if your temperature is being given in degrees C, to turn it into Kelvin, you add 273. Next topic we'll take a look at is polar and non-polar molecules. So the first thing we need to talk about is what causes dipoles in covalent bonds. So they're caused by a significant difference in electronegativity values of those bonded atoms. So typically anything greater than 0.4 of a difference will mean that the bond is polar. The only bond that you need to class as non-polar that has different atoms in is the CH bond, and that's because the difference is 0.4. So that's not significant. So the CH bond, even though it's different atoms, is classed as a non-polar covalent bond. So what causes the overall molecule to be polar or non-polar? Well, we'll start with symmetrical molecules. They're generally non-polar, and that's because the polar bonds are arranged in a way that the individual bond dipoles cancel each other out. So there's no overall dipole on the molecule. There's 3 examples for you: CO2, CCl4, SF6. So if you've got a non-symmetrical molecule, they are polar, and that's because the individual bond dipoles don't cancel out. So what causes a molecule to be non-symmetrical? So asymmetry is caused by the presence of different terminal atoms. So what do I mean by that? Different atoms around the central atom. So there's an example there, CCl3F. So you can see you've got 3 chlorines and a fluorine around the carbon. So that's going to be a polar molecule. The other thing that can cause a molecule to be polar is the presence of lone pairs around the central atom. So SO2 is polar. Remember, CO2 is non-polar. So SO2 is polar because there's a lone pair on the sulfur. Now there is one exception where you've got lone pairs around the central atom and the molecule is non-polar, and that's XeF4 xenon tetrafluoride. So there's a picture of it there. So you can see that the fluorine atoms are arranged sort of around the middle there in a sort of square plane away, and the 2 lone pairs that are on the central xenon, one's pointing up and one's pointing straight down. So their effects cancel each other out. So that molecule would be non-polar. Next topic we'll look at is electron structure. Straight away I'm going to start with the most common mistake: students basically mixing up subshells and orbitals. So the rule is orbitals can only hold 2 electrons. There's 2 orbitals you need to know the shape of. So s orbitals, they have a spherical shape. P orbitals have what's called a dumbbell shape. So it's like a figure of 8. There's an upper part and a lower part, but both parts are the orbital. S subshells can hold 2 electrons. P subshells can hold 6 electrons. So that's where that common mistake comes from. I think as soon as a student sees P, they just think 6. But if it's the orbital, it's got to be 2. D subshells can hold 10 electrons. D orbitals, 2 electrons. F subshell, 14 electrons, but in F orbital, 2 electrons. And then when subshells fill up, the orbitals half fill first, and the spins go in the same direction. So you can see in the bracket there, I've got those 3 arrows, so that would represent a p subshell with 3 separate p orbitals, so the spins would be up, 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 all the same direction. And then you would start pairing them up. So you can see now it's up, down, up, down, up, down. And the last thing to say is the 4s subshell fills before 3d. Next topic we'll look at is enthalpy changes. So first thing we'll say is to calculate the delta H, the enthalpy change for a reaction from mean bond enthalpy values. I call it the in minus out method. So the energy in is the energy needed to break the bonds between the atoms in the reactants. The E out, the energy out, is the energy released when bonds between atoms are formed in the products. So remember it this way, bendo-exo, breaking is endothermic, energy has to go in. Making is exothermic, energy is released. Really common mistake in this is students saying energy is needed to make bonds. It is not. So energy is not needed to make bonds. It's an exothermic process. A reaction will be exothermic if the energy released is greater than the energy has to go in, and it'll be endothermic if the energy that has to go in is greater than the energy that comes out. If you're calculating the enthalpy change for a reaction from experimental calorimetry data, it's Q equals mc delta T. So the Q is the energy transferred to the surroundings. So often it's a solution in a beaker or water in a beaker. You then, once you've got your Q, you change that into kilojoules, and then to get delta H, the Q in kilojoules is divided by the moles involved in the reaction. The M in the mc delta T calculation is the mass of the liquid that the thermometer's in. Often students pick the wrong mass. So wherever the thermometer is, that's the mass we use in Q equals mc delta T. Delta H values from experimental calorimetry results will often be different to the data book values. They're often a lot lower, and that's due to heat loss to the surroundings, the reaction not being carried out in standard conditions in the lab, incomplete combustion if you are combusting alcohols, and the specific heat capacity of the apparatus has been ignored. When you're calculating enthalpy changes for a reaction using combustion data, it's reactants minus products, and the way I remember that is crap. If you're calculating delta H for a reaction using formation data, it's products minus reactants, and I remember that using the word faux. Don't forget to multiply delta H values by the number of moles in the equation. And delta H values must have a sign. So it's either positive if it's endothermic or negative if it's exothermic. So remember, when you're doing the calculation, your calculator will not put a positive sign in front of your final answer. Obviously, for an endothermic reaction, don't forget the positive sign. Obviously, if it's negative, the calculator will put the negative sign in for you. Moving on to enthalpy changes of neutralization. So that's the enthalpy change for a reaction between an aqueous acid and alkali to form 1 mole of water. So in other words, we're talking about this reaction, H plus ions plus OH minus ions, obviously aqueous, making a mole of H2O. The enthalpy change of neutralization for all strong acid-alkali combinations is around the minus 57 kilojoules per mole mark. And that's because basically all strong acids and alkalis involve the ionic equation that's directly above. And for weak acid-alkali combinations, the enthalpy change of neutralization is less exothermic than minus 57 kilojoules per mole because these are only partially ionized. So some of the energy is being used to ionize the acid or alkali. If you're devising a calorimetry experiment to determine the enthalpy change of neutralization, it's best to go for concentrations and volumes of the acid and alkali so the moles of the ions are the same. And in terms of concentration, it's best to use either 1 or 2 moles per decimeter cubed, nothing lower, nothing higher, so you get a decent temperature rise that can be recorded. So moving on to the calculation, same as before, Q equals mc delta T first. That gives you the energy change in joules for the reaction. Change it straight away into kilojoules. The M is the mass of solution, and it's the combined volumes of the acid and alkali. So if you use 35 cm cubed of each chemical, then the mass of the solution is going to be 70 grams. The delta H is the Q in kilojoules divided by the moles of water formed. Remember, in the definition, it's the enthalpy change per mole of water formed. So we divide by the moles of water. And don't forget your sign, but this one is always negative because neutralization is an exothermic reaction. Sticking with enthalpy, we'll look at Born-Haber cycles now. So state symbols are absolutely essential in Born-Haber cycles. Don't forget to include electrons. Often students forget to include electrons when it gets to the ionization energy stage. If there's 2 moles of something in a cycle, don't forget to double the enthalpy change because enthalpy changes are per mole. And remember, you can only perform 1 change per step. Arrow direction, so a downwards arrow in a Born-Haber cycle is for an exothermic process, and upwards arrow is for an endothermic process. For enthalpy change of solution cycles, make sure you can draw both types. So there's an exothermic one and an endothermic one. But in terms of the calculation, doesn't matter what type of cycle it is, enthalpy change of solution is always the sum of the enthalpy changes of hydration minus the lattice enthalpy. Both lattice and hydration enthalpies are affected by ionic radius, not atomic radius, and ionic charge. The smaller the ionic radius, the more exothermic the lattice and hydration enthalpies will be. And finally, the greater the ionic charge, the more exothermic they'll both be. So we'll move on to standard electrode potentials now. It's quite a lot on this slide. So first of all, standard electrode potential half equations are conventionally written as reduction processes. So gain of electrons. Electrons are on the left. The oxidizing agent, the electron acceptor, is the species or combination of species on the left-hand side. The most powerful oxidizing agent is the species or combination species on the left, but they've got to have the most positive standard electrode potential. So obviously that's going to be supplied in a table. And then moving on to reducing agents, they are electron donors. So they are the species or combination of species on the right now. And the most powerful reducing agent is the species on the right with the least positive standard electrode potential in the table. Now, often you have to construct the overall cell reaction, so that's when you combine the two half equations together from the two systems. So the half equation with the most positive electrode potential moves forwards, accepts the electrons. The one that's the least positive moves in reverse and donates electrons. And remember, the electrons must cancel, so you might have to multiply out one or both of the half equations to make that happen. The most positive electrode potential is the positive electrode in the cell. Least positive is the negative electrode. And then to calculate the voltage of the cell or the E cell, it's most positive electrode potential minus least. And just remember that if a half equation did need to be multiplied out to balance the electrons, you don't multiply out its electrode potential value. If you've been asked to draw the cell that's used to measure the electrode potential value, then it's the one where you draw it alongside the standard hydrogen electrode, so make sure you know how to draw that. The salt bridge allows a flow of ions, remember, so that's typically just a piece of filter paper soaked in an electrolyte, so the classic example is potassium nitrate, so it allows the K plus ions and NO3 minus ions to flow into the beakers to balance out the charge difference that builds up. And just remember, when you draw in the diagram, that your salt bridge actually goes into your solutions. Last couple are about fuel cells and storage cells or batteries. So fuel cells, remember, have reactants supplied continuously to the cell, whereas a storage cell or battery the reactants have to be stored within the cell. And finally on this slide, standard conditions, remember, are temperatures 298 Kelvin, or you could say 25 degrees C, pressure 100 kilopascals, and any solutions must be at 1 mole per decimeter cubed. So moving on to the equilibria topic, so Kc and Kp. So in terms of expressions, it's always products on the top divided by the reactants. Square brackets for Kc expression, so that means equilibrium concentration in moles per decimeter cubed. Curved or no brackets for Kp. And if you're calculating the equilibrium constant, you must always give the units. Kp expressions only include gaseous species. If Kc or Kp is greater than 1, the equilibrium position is to the right or on the product side of the equilibrium. If it's a double greater than sign, it means it's significantly on that side. And then the opposite, if it's less than 1, equilibrium positions to the left, so on the reactant side, and the double arrow significantly so. A couple of checks you can do during Kp calculations. So partial pressures should always add up to the total pressure, and the mole fraction should always add up to 1. And remember, the value of Kc and Kp is only altered by changes to the temperature. So if you do change the temperature, the reactant and product concentrations or partial pressures have to change to give the new value of the equilibrium constant, and that's achieved by an equilibrium shift. Moving on to the transition elements topic. So a transition element forms at least one ion with an incomplete d subshell. Scandium and zinc are not transition elements, and that's because scandium only forms the Sc3+ ion, so it doesn't have any d electrons at all. Zinc only forms the Zn2+ ion, so that's got a 3d10 configuration, so it doesn't have a partly filled d subshell. Sticking with electron configuration, remember copper and chromium are unusual because they have a 4s1 configuration rather than the normal 4s2 for all the others. When any transition element forms an ion, so they always form positive ions, lose electrons, but they lose electrons from the 4s subshell before any come out of 3d. General properties now, so as well as the usual metallic properties like conductors of heat, conductors of electricity, they have these 4 general properties: variable oxidation states, they form complex ions, they form coloured compounds, and they can act as catalysts, and catalysts can be homogeneous or heterogeneous. A little bit about reactions now. So all aqueous transition metal ions, so there's an example there, CuH2O6 2+, they all produce hydroxide precipitates when you add a small amount of aqueous hydroxide ions. Only the chromium 3 hydroxide precipitate dissolves in excess, and that gives that ion there, CrOH6 3-. You get the same reaction taking place when you add aqueous ammonia, because effectively you're adding ammonium hydroxide. So all aqueous transition metal ions produce hydroxide precipitates with a small amount of aqueous ammonia, and this time 2 of them dissolve in excess, so that's copper 2 hydroxide and chromium 3 hydroxide again, and there's the respective products there. Last thing on this slide, know your colours. I know it's a pain, but you really do need to know all the colours of the transition metal ions. So moving on to isomerism in transition element complexes. So we'll start with 4 coordinate complexes. So these are the ones of platinum. Just got to remember that they are square planar. So we've got cis and trans platinum. So you can see here that in the cis version, the identical ligands are 90 degrees apart, whereas in the trans version, they are 180 degrees apart. Moving on to 6 coordinate complexes. So the first thing you do is start with an empty octahedron. So that's that new diagram there. You would then attach your ligands via the correct atom. If you've got 3 bidentate ligands, complexes will show optical isomerism. So you would just show the mirror image of whatever you've drawn. If you've got 2 monodentate and 2 bidentate ligands attached, the trans version, so that's where the identical ligands are 180 degrees apart, they don't show optical isomerism, However, the cis version, so that's when the identical ligands are 90 degrees apart, they do show optical isomerism. So we'll look at some practical stuff now in the form of the qualitative analysis of ions, and starting with cations. To test for the ammonium ion, you would add hydroxide ion, so sodium hydroxide aqueous, warm gently, and then you test the gas produced with damp red litmus. The observation for that is the litmus paper turns blue, and the equation looks like that. And I would always do ionic equations for these reactions. Moving on to the copper 2 plus ion, so you'd add aqueous hydroxide ions. Again, aqueous sodium hydroxide is fine until in excess. Get a pale blue precipitate which is insoluble in excess sodium hydroxide. There's the equation for that one. You can give the more detailed equation if you want, but you don't have to. The simple equation's absolutely fine, so I'm just going to limit it at that. Manganese 2 plus ions, same procedure as copper 2. You get a light brown or beige precipitate which is insoluble in excess sodium hydroxide. There's the equation for that one. Aqueous ion 2 plus, same as before. This time we get a green precipitate which is insoluble in excess sodium hydroxide. There's the equation for that one. Moving on to the aqueous ion 3 plus ion. Same again, but this time we get an orange-brown precipitate insoluble in excess sodium hydroxide. There's its equation. And the chromium 3 plus ion, same as before. This time we get a grey-green precipitate at first, but it's soluble in excess sodium hydroxide and it gives a green solution. So the first equation looks like that. The second equation looks like that. So we'll move on to qualitative analysis of the anions now. So starting with the carbonate ion. So you would add dilute acid. Nitric acid is normally the one that's used. You test the gas produced by bubbling through lime water. So obviously you've got a gas produced, so you're going to see bubbles, or you could say effervescence, and the CO2 will turn lime water cloudy. The equation looks like that. To test for aqueous sulfate ions, you would add a source of Ba2 plus ions, so barium nitrate's a good example there. You get a white precipitate, and there's the equation for that one. And finally the halide ion tests. So the test is to add silver nitrate solution followed by aqueous ammonia. Now I'm going to go into this in a bit more detail on the next slide, but for that test nitric acid's often added first to remove any carbonate ions that you might have present, but I'll mention more about that later. So observations, you get a white precipitate of silver chloride which is fully soluble in dilute aqueous ammonia. Cream precipitate of silver bromide which is soluble in concentrated aqueous ammonia. It's only partially soluble in dilute aqueous ammonia. And you get a yellow precipitate of silver iodide which is insoluble in concentrated aqueous ammonia. So we'll just finish with the equations, all very, very similar. So there's the chloride one, there's the bromide one, and there's the iodide one. So we'll finish with a look at the correct order for the anion tests. So if you're testing an unknown substance, the tests need to be carried out in a specific order, and the order is carbonate first, then sulfate, then halide. Now I remember that as the cash order. That is not an official chemistry term, it's something one of my students made up. So don't talk about the cash order because the examiner probably won't have a clue what you're talking about. So carbonate, sulfate, halide. So we'll just look at some scenarios if you carry out the tests in the wrong order. You get these false positive results. So if you added barium 2 plus ions to carbonate ions, so you're effectively performing the sulfate test because you're putting barium 2 plus ions in, you're going to get a white precipitate of barium carbonate, but you're going to think that you've got a sulfate because you've added barium 2 plus ions and you've got a white precipitate. But it's actually that reaction that's caused the white precipitate. So that's what we call a false positive. Another example is if you added aqueous silver ions to carbonate ions. So you're effectively carrying out a halide test. You're going to get a yellow-grey precipitate of silver carbonate. So because you're doing the halide test, you've got a yellowy coloured precipitate, you're going to think you've got an iodide present. And you haven't. That's what's happened. you've actually got a carbonate that's produced that precipitate. So that's why on the previous slide, in the halide test, you tend to add nitric acid first to remove any carbonate ions that might be there. And then the other example of a false positive is if you carry out the halide test, but there's sulfate ions in the test tube, you're going to get a white precipitate of silver sulfate. But you'll think that you've got silver chloride, you've got a chloride present, but that's the reaction that's taken place. So when you're dealing with unknown ions, you carry out the tests like this. Carbonate test first. If that's negative, move on to the sulfate test. If that's negative, you can move on to the halide test. So we'll move on to the organic topics now, and we'll start with the alkanes. So alkanes are unreactive due to the relatively high bond enthalpies of the bonds. So we've got CC single and CH bonds in an alkane. Also, the CC single and CH bonds are classed as non-polar. Obviously, CC bonds are non-polar, CH bonds classed as non-polar because the electronegativity difference is so low. You've got 4 sigma bonds around each carbon atom in an alkane, which gives it a tetrahedral arrangement, and the bond angle is 109.5 degrees. Sigma bonding involves end-to-end overlap between 2 orbitals, and because it's along the axis of the bonds can rotate freely. Alkanes undergo complete combustion if there's lots of oxygen, making carbon dioxide and water, but it's incomplete combustion if there's not enough oxygen, so you can get either carbon monoxide or carbon particulates and water. They react with halogens in the presence of UV radiation via the free radical mechanism. There's 3 steps to that: initiation, propagation, termination. And remember, initiation involves the homolytic fission of the halogen covalent bond, and homolytic fission is the breaking of a covalent bond where each atom receives 1 electron, and that produces free radicals. The mechanism is bad at making a single organic substance, and that's due to multiple termination steps. Substitution can continue, so further substitution, and substitution can be anywhere on the carbon chain. Moving on to the alcohols topic now. So alcohols contain the hydroxyl group, not the hydroxide group. Alcohols can form hydrogen bonds with water because obviously the lone pair on the O of the hydroxyl group can hydrogen bond with the H of a water molecule and vice versa. They can be primary, secondary or tertiary, so make sure you know what type of alcohol you're dealing with if you're answering a question on alcohols. Primary and secondary alcohols can be oxidized by heating with acidified dichromate 6 ions. Don't forget the acidified, and the colour change for that reaction is orange to green. The oxidation products from the primary alcohol's oxidation depends on the heating method used. So if you heat by distillation, basically you're taking the aldehyde product away from the oxidizing agent and you end up with just the aldehyde. If you do it under reflux, the aldehyde drops back into the heating flask and it gets oxidized to the carboxylic acid. When you're writing equations, remember that water is only made in the first oxidation when the aldehyde's made. If you oxidize a secondary alcohol, you can only make a ketone, so it's a lot simpler. And obviously tertiary alcohols can't be oxidized. When you heat an alcohol with a mixture of a sodium halide and sulfuric acid, it's going to make hydrogen halide, and then that reacts with the alcohol, and the OH group, the hydroxyl group, substitutes for whatever the halide is. When you heat an alkene with a strong acid catalyst, H2O, I always tell my students to think of it as HOH. So H2O is eliminated and that makes an alkene. And the thing to remember is the hydrogen, the single hydrogen in the HOH, is removed from an adjacent carbon to the OH carbon. So where those 2 carbons are, the one with the OH on and the adjacent carbon, you're going to get a double bond forming there. You get the alkene. And whenever you make an alkene in any reaction, you should always ask yourself, can it show EZ isomerism? We'll take a look at some nitrogen compounds now, followed by optical isomerism. So starting with amines. Amines can be primary, secondary or tertiary. Amines act as bases, so they accept H plus ions by using the lone pair on the nitrogen, and that's going to form a coordinate bond. The nitrogen's providing both electrons in the covalent bond with the H plus ion, and that generates ammonium salts. Primary aliphatic amines can be made by reacting haloalkanes with an excess of ammonia, but the ammonia needs to be dissolved in ethanol, and the excess ammonia avoids further substitution to secondary and tertiary amines. If you want to make an aromatic amine, that's done by reducing a nitroarene with a mixture of tin and concentrated hydrochloric acid. Don't mix up the reducing agent. Remember, you've seen NaBH4 used to reduce carbonyl compounds to alcohols. We use a different reducing agent to reduce a nitroarene, so just watch out for that one. In the reaction, you need 6 moles of reducing agent per NO2 group reduced. You can also make amines by reducing nitriles. I've got a slide about nitriles coming up, and we use hydrogen and a nickel catalyst for that one. So the CN, the nitrile group, becomes CH2NH2. So you can see you've got 4 more hydrogens there, so you need 2 moles of hydrogen in the equation. We'll have a quick look at amides now. So amides can be primary, secondary or tertiary. So that's what they look like. Most common mistake I see is students mixing up the amide group for the amine group. So just be careful with that. So an amide has a nitrogen directly bonded to a C double bond O, whereas an amine just has the nitrogen directly bonded to the carbon group. And the other thing we need to know about amides is, just like the ester group, the amide group can also be hydrolyzed by hot aqueous acid and hot aqueous alkali, and it's this CN bond that breaks. Moving on to amino acids now, more specifically alpha amino acids. They're the ones we look at. They have the NH2 and COH groups bonded to the same carbon atom. So that means they have that general formula. They all show optical isomerism except glycine. That's where the R group is just a hydrogen. I've got a more detailed slide on optical isomerism coming up, so I won't say any more about that. In terms of reactions, the carboxyl group can react with alkalis, so that'll generate a carboxylate salt. The carboxyl group can also react with alcohols in the presence of concentrated sulfuric acid, so that's going to generate an ester group. And the NH2 group can react with acids. Remember, the nitrogen's got a lone pair on it, can accept H plus ions from acids and generate ammonium salts. And the sort of top tip really there is beware of the carboxyl groups and NH2 groups in the R group, because they will also react with those things as well. And the last nitrogen compound we'll look at is the nitriles. So nitriles contain the CN functional group, so there's a triple bond between the carbon and the nitrogen. They're formed by reacting haloalkanes with ethanolic cyanide ions. So all that means is the source of cyanide ions is dissolved in ethanol. It's just a solvent that helps the chemicals mix together better. You can also make the nitrile group by reacting a carbonyl compound, so an aldehyde or a ketone, with hydrogen cyanide. But that's going to make the hydroxynitrile. So what can you do with nitriles? Well, you can turn nitriles into amines by reducing them, and that's by reacting with hydrogen and a nickel catalyst. You can also hydrolyze them into carboxylic acids, and that's done by reacting them with an aqueous acid. So, for example, a mixture of HCl and water. And now, as promised, some slides on optical isomerism. So it's a form of stereoisomerism, so that means they've got the same structural formula but different spatial arrangements of the atoms or groups. Optical isomers are described as being non-superimposable mirror images of each other. They're also known as enantiomers, and it's possible if the molecule has what's called a chiral center. So that's where you've got a carbon atom in the molecule with 4 different atoms or groups attached. For each chiral center in a molecule, there's a pair of optical isomers possible. So the total number of isomers possible is 2 raised to the power of the number of chiral centers. So we'll have a quick look now at how you draw optical isomers. So the first thing you do is identify the chiral center. I'll show you all this in a second. You then draw what I call an empty tetrahedral structure. You add your atoms or groups, and then you do the mirror image of what you've drawn. So there's a structural formula. So we identify the chiral center. It's that carbon there. So we just draw an empty tetrahedron, and now what I need to do is start adding groups. And it doesn't matter which way around you do them, so long as your mirror image is a reflection of what you've drawn. So the right hand molecule must be the mirror image of the left hand one. You could be asked about a 2 chiral center molecule, so there would be 4 possible optical isomers, the one on the screen now. So how do you go about doing the others? So the sort of logical approach I would take is mirror both of your chiral centers. So you can see that chiral center is the mirror of that one's the mirror of that one. Then you could just mirror the top, and then you could just mirror the bottom. So we'll take a look at carbon-carbon bond formation now. So one of the reasons why this is carried out is to extend the length of the carbon chain. So I'm going to give you a couple of examples to illustrate this. So if you look at that one there, we're starting with 2 carbons and we're going to 3. So obviously we've got to grow the carbon chain. So the way we do that is we generate the nitrile functional group by reacting with ethanolic cyanide ions. Once we've done that, we've obviously got 3 carbons into the chain. We then react that nitrile with a hydrogen nickel catalyst mixture, and that'll turn it into the amine that we want. The other example I've got is going from a haloalkane to a carboxylic acid, but the important thing here is we're going from 2 carbons to 3. So we do the same thing again at first, generate the nitrile functional group, and then we would react it to get the carboxylic acid with aqueous HCl. You also see carbon-carbon bonds formed when carbonyl compounds react with hydrogen cyanide, and that generates a hydroxynitrile. And you also see carbon-carbon bonds formed in the alkylation and acylation reactions with benzene rings. So if you take benzene, react it with a chloroalkane in the presence of an AlCl3 catalyst, you will form a carbon-carbon bond off the benzene ring. Likewise, benzene with an acyl chloride and the same catalyst will also form a carbon-carbon bond off that benzene ring. So we're into the last section now, you'll be pleased to hear, and we're going to take a look at some practical stuff, starting with synthesis of an organic solid. So you would purify your organic solid by recrystallization. So how do you do that? You dissolve your solid in the minimum volume of hot solvent. You would then cool it back down again to recrystallize, and the impurities that are present would stay in solution. You would filter using Buchner apparatus, or you could call it reduced pressure filtration, which looks like that. And a couple of years ago they actually asked people to draw that, so make sure you know how to draw it in case it's asked again. You would wash with cold solvent now, because obviously if you use hot solvent your sample is going to dissolve and you don't want that. So wash with cold solvent and then you allow it to dry. How do you determine purity? Well, very similar to before, but this time we measure the melting point and we compare to known data values. It should match the data closely. It should melt sharply, i.e. over a narrow range. Or you could do those 3 things there. Next couple of slides is just looking at how you draw the quick fit apparatus. So we'll start with distillation. Some key things to point out here. So obviously you've got a flask with some chemicals in. You need a heat source, thermometer. Make sure your bulb of your thermometer is in line with the central part, the central tube of the condenser. Obviously this is your condenser here. Make sure you get the water flow direction right. So water always goes in at the bottom of a condenser and it comes out at the top. If you get it the wrong way around, the condenser doesn't fill up efficiently. So you get like air bubbles in it. So it goes in at the bottom, out at the top. And then a beaker, a container to collect your distillate. So that's what comes off distillation. And make sure that's not sealed up. Okay, so it needs to be left open. Moving on to reflux apparatus. So some key things here. Obviously a flask. Come do a pear-shaped flask if you want. Heat source. Just make sure there's no gaps here so that the vapours as they form go up the central part of the condenser. You've got the water in at the bottom, out at the top, and a key thing on this one is make sure you leave the top of your condenser open. That should never ever be blocked off. Next slide's just going to run through the tests for the various organic functional groups. So here we go. So alkenes reacting with bromine, the bromine is decolorized. I hope you can appreciate what I've done there. Took me about 3 minutes to do that. You're welcome. Carboxylic acids, you add sodium carbonate and you get bubbles forming, which is CO2. Primary and secondary alcohols, you can heat them with acidified dichromate 6 ions and you get the orange to green colour change. Remember, aldehydes can also be oxidized, so they will give that same response there. Haloalkanes, you can react them with aqueous silver nitrate in ethanol, and the observations for these. Chloroalkanes will give you a white precipitate of silver chloride. Bromoalkanes, a cream one, and an iodoalkane will give a yellow precipitate of silver iodide. Moving on to phenols, there's several ways to test for a phenol. The one I always go for is this one. You test the acidity by pH measurement. Remember, phenols are very, very weak acids, so they should be indicated as acids by that. Then you could add sodium carbonate and you don't get any bubbles. So remember, carboxylic acids are really the only other acidic substance we look at A level. So they're acidic, they will give bubbles of CO2, whereas a phenol is acidic, but it won't give bubbles of CO2 with sodium carbonate. Another thing you can do is react a phenol with bromine, and the bromine is decolorized and you get a white precipitate. Another thing you could do is you could react it with FeCl3, iron 3 chloride, or ferric chloride it's also called, and you get a violet purple solution. Moving on to carbonyl compounds, you would add 2,4-DNP and you would get an orange precipitate. So if you did that test, you would then know that you've either got an aldehyde or a ketone present. So how could you differentiate between those two? Well, aldehydes you could heat with Tollens reagent, so that's ammonia and silver nitrate solutions, and you get a silver mirror. To determine if you've got a ketone, you would add 2,4-DNP to get that orange precipitate to confirm it's a carbonyl, and then you'd add Tollens and you wouldn't get a silver mirror. Moving on to chromatography, so starting with thin layer chromatography, TLC. So the separation is achieved by relative adsorption. Just be careful there, you don't say absorption. So the different components in your mixture will bind to the solid stationary phase by differing amounts. So if it's strongly adsorbed, it's not moved as far up the plate as one that's weakly adsorbed. That gives you an RF value, which you can measure by taking the distance travelled by the spot and dividing by the distance travelled by the solvent, which is obviously your mobile phase. How do you know what you've got? You compare the RF value of your substance with known data values, or you could run a chromatogram alongside that of a known substance and compare them. Moving on to gas chromatography, or GC for short. So separation there is by relative adsorption if the stationary phase is a solid, so that works exactly the same way as TLC. But if you've got a liquid stationary phase, which you can have in gas chromatography, it's by relative solubility. GC measures retention time, so that's the time it takes from injection to detection. How do you know what you've got? You compare the retention time of your sample with known data values. So on a gas chromatogram, the different components in the mixture give peaks with different retention times, and they have a measurable area. Don't worry, you don't have to measure the area, you would be given that. And the area under the peak is proportional to the relative amounts of the component in the sample. And the relative proportions are measured by dividing the area under a particular peak by the total area under all of the peaks. If you wanted to know the actual concentration of a substance in a mixture, you would use a calibration curve. So the way you do that is you measure the area under a peak for known concentrations of that substance. You would then use that data to plot a calibration curve. Then to find the concentration of the sample in your mixture, you would compare the area under its peak with the area on the calibration curve, and obviously that correlates to a particular concentration. So you'll be pleased to hear that's it. I hope that was helpful, and really all that's left for me to say is the very, very best of luck. Remember, we can do this! Ha ha! See you folks, bye.